That's great.
Okay. Yeah. First of all, I would like to welcome everyone to this workshop. Today, I will be talking about one of the use cases in 5G Heart project, which is automatic colon cancer diagnosis with capsule camera. I am Hemin Qadir. I'm an AI research scientist at Oslo University Hospital. And some of the slides will be presented by Ilangko Balasingham. He's the head of section and professor of medical signal processing and communications at Oslo University Hospital and NTNU. So this is the outline of my talk. In the beginning, I will introduce colorectal cancer. I'll briefly define what's this cancer, and then I'll talk about colonoscopy. Then I will move to talk a little bit about wireless capsule endoscopy. Then I will introduce you artificial intelligence, machine learning, and deep learning. Then I will talk about deep learning in automatic polyp detection. Then I will come to our use case, which is cloud-based polyp detection, and then I will talk about the interaction that we have established between the AI running in the cloud and a capsule camera that's moving in the colon. Then I will show some of the results. Then I will conclude my talk at the end. So colorectal cancer is the third most common cancer, and the main cause of this cancer is this mushroom-like growth in the inner side of the colon. Those polyps do not make any symptoms in the beginning, and they are not cancerous. But if they are left untreated in the colon, they will become cancer and life-threatening. So it's important to detect them and remove them before they become cancerous. So around 12 to 50% of both genders above the age of 55 years are at the risk of getting colorectal cancer. So it's recommended for this group of people to undergo colon screening, regular colon screening, for example, annual colon screening. Currently, colonoscopy is the gold standard for colon assessment. As you can see it here in the picture, a medical doctor inserts a tube into the colon, investigating the colon, trying to detect abnormalities in the colon. And this tube is equipped with a camera, light, and some other tools that help the clinicians to remove and take out the polyps. But colonoscopy is a human-dependent procedure. That means it depends on how experienced the clinicians are. So it's been reported that polyp miss rate is around 25%, and those missed polyps may become cancerous over time. And then the survival rate becomes only 10%. Colonoscopy is, however, suboptimal for population-based screening because of the shortcomings that comes with the colonoscopy procedure. As I explained it in the previous slide, it's human-dependent procedure, so it's prone to human error. And a single procedure takes quite a lot of time. It may take 30 minutes to 1 hour, and it's also inconvenient for the patients. And in some countries, for example, the USA, it's a very expensive procedure. So wireless capsule endoscopy can be an alternative for population screening. It has several advantages compared to colonoscopy. For example, it's more convenient and it's going to be cheaper than colonoscopy. But of course, it has some disadvantages that limit the use of wireless capsule endoscopy for population screening. For example, the video that's captured by this pill camera is too long, and an expert needs to sit and investigate the entire video offline. And the image quality is low, and the camera has low frame rate. So to make wireless capsule endoscopy an optimal solution for home-based screening program, we need to develop an automatic video analysis that can automatically detect polyps in the colon. Then this method will be available for everyone, and it will be acceptable and cheap. So in the past few years, deep learning has shown promising results for automatic polyp detection. As you can see it here in this figure, deep learning is a subset of machine learning, and machine learning itself is a subset of artificial intelligence. And artificial intelligence can be defined as a program that can sense, reason, act, and adapt. Machine learning can be an algorithm that can learn patterns, different patterns from data. But deep learning can be a multi-layered neural networks learn from a vast amount of data. So here I'm showing a typical deep neural network that consists of 4 layers: one input layer, 2 hidden layers, and an output layer. The input layer takes in this image, and these 2 hidden layers are trying to find some patterns in the input data and predict the output. So this is a very small network, but a deep neural network can comprise of hundreds of thousands of neurons organized in distinct layers. So higher quality video recording and higher frame rate can facilitate the development of better automatic polyp detection. But the issue with the camera, with the pill camera, is that we have limited onboard battery. The camera cannot maintain capturing high quality videos with very high frame rate, as it dramatically drains the onboard battery. So someone can think of controlling the operative parameter of the camera, letting the camera to capture higher quality with higher frame rate for a short period of time. But of course, this cannot be done manually. We need to do that automatically. So with the use of an AI, this can be implemented automatically. But we need to establish on-the-fly interaction between the deep learning model and the camera that's moving in the column. So as you can see it here in this figure, the AI model can receive the frames from the pill cam, analyze the frames, trying to detect the polyps. Once a polyp is detected, or let's say a candidate is detected, then the model can generate some signal, controlling signals, sending back to the camera in order to change the operative parameter of the camera, just to make sure that this is a polyp or not. But right now, local on-the-fly algorithm is impractical because of the limited onboard battery and on-belt processing power. So what's the solution for this is to implement the AI algorithm remotely so that we can train it and improve the performance in the cloud and use it to analyze video. But to do that, then we need to make a very efficient link between the capsule and the cloud, where we have the AI running. So a 5G network enables the use of cloud edge computing because of the high data rate. A 5G network has a very high data rate, and that allows us to establish a real-time link between the camera and the cloud with minimum latency. So this use case consists of 2 parts. The first part is about backscatter communication, and the second part is to develop an AI that's running in the cloud, detecting polyps in real time. I'm not going to talk about the backscatter communication because I don't know so much about this. Another group is working on that, so I will let Ilangko to briefly describe this part of the project. Ilangko?
Yes, thank you, Hemin. So I just wanted to say a few words about the backscatter communication. So we have, so as you mentioned, as Hemin mentioned to you, that this pill camera, which has camera and microcontroller and a transmitter. So normally it takes 8 to 12 hours. So normal, the pill, current version of the pill is transmitting extremely low data rates just because it is using an onboard battery. So this method that we have developed as part of several other projects, but it's going to be used to demonstrate the concept in this project also, that we could also send the images from this pill to, using a camera there and using something called backscatter communication. So most people here know understands that what backscatter communication is. It's pretty much like RFID communication, but yes, you know that RFID does not support high data rate communication. Even it is an active communication, it cannot have high data rate. Here it's about the data rate can be up to 15 megabits per second. And the depth, like how far this is from the skin, it could be around 15 centimeters. So developing this method is a pretty unique way that we have done. I will not go too much into the details here. The interesting part for us in this project is to see whether we could transmit data from this pill through this system and using the electronics that's shown here with an on-body antenna system that you see on this figure, and then to transmit the data through the 5G modem to the cloud. And once Hemin is able to analyze using his AI algorithms, the interesting part is for us to see whether we could alter the camera parameters, like, for example, the spatial resolution of the camera or the frame rates, or maybe in the future we could also use different lights. So I will not go too much into detail, but this part of the project is not completely finished yet. So we will not demonstrate this part today, but Hemin will explain how this happens when it comes to a video that is available and doing the streaming over the 5G network to a edge computer with the AI implemented. So Hemin, please.
Okay, thank you, Ilangko. Yeah, so the second part of this use case is to establish a connection between the PillCam and the AI server running in the cloud. So this is the setup configuration that we use to measure end-to-end video streaming latency. As you can see it here, because the PillCam is not quite ready, I used a PC to stream the video. So I used that PC to simulate a PillCam. And then I used this CPE modem provided by the Telenor to connect this video streamer to the Telenor's 5G Vini network. Then I used another CPE modem to connect the server to the same network. And then I measured the end-to-end latency. So the end-to-end latency is the time required for a frame to travel from this PC, from the video streamer, all the way to the server. So this table shows the result that we obtained from the setup that I showed you in the previous slides. As you can see it here, UDP protocol, RTP protocol, which is based on UDP protocol, provides the lowest latency, and it's around 46.74 milliseconds per frame. But when I use TCP, RTSP protocol, you see that the latency is quite high, and the same thing for HTTP. That's because TCP is connection oriented. Whenever a frame is received by the destination sends an acknowledgement back to the sender, telling that the package successfully, without any corruption, has been received. But UDP is connectionless, so the sender send out packages without waiting for acknowledgement from the destination, and that's why you see this difference. But the problem with UDP is that it's not a reliable protocol, because there's no two-way communication between the sender and the receiver. So whenever we have a corrupted frame, received by the destination, there's no any other way to tell the sender to resend that frame because this frame is corrupted. And this will make problems for the AI because the AI needs high quality frames. So right now, we are in the phase of using other protocols, for example, Apple HLS protocol or MPG- protocol. And this is the AI model that we've been developing to analyze the video frames. As you can see it here, this is a UNet-based encoder-decoder network. So the yellow blocks belong to the encoder and the green blocks belong to the decoder. The encoder receives a frame, extract the features, and store the features in the bottleneck layer. As you can see it here, this bottleneck layer is located between the encoder and the decoder, storing the extracted features. But originally, this type of networks, these encoder-decoder networks are developed to analyze a single frame. But it's well known that deep learning is vulnerable to small changes, to small noises. Therefore, the network makes or produce unstable output. The same network can detect the same polyp in some of the frames and miss the same polyps in a series of consecutive frames. So to solve this issue, we adapted this model so that we can incorporate temporal information, not temporal information, because temporal information is very important information for video analysis. So we decided to split the bottleneck layer based on how many previous frames we're going to consider. So if we want to consider the first previous frame, we split this bottleneck layer into two. The first one to store the extracted features of the current frame, and the second split is to store the extracted features from the first previous frame. And in case if we want to consider more, then we split the bottleneck layer equally to store the features of the extracted features of the consecutive frames. Here you can see some of the results that we obtained. We measured the performance of the models in terms of sensitivity and precision. So sensitivity is a ratio of true positives to the total number of polyps in the test set, multiplied by 100. And if we want to write it in a mathematical formula, we can say that it's equal to the number of true positives, the number of truly detected polyps, over the number of true positive plus those polyps that are missed by the model. And precision measures the ratio of true positives to the total number of detected regions, including false positives. So if we write it in a mathematical formula, we will have true positives divided by true positives plus false positives multiplied by 100. As you can see it here, when we only use the current frame to detect the polyps, you see that the model is able to show very high sensitivity, but precision is very low. That's because the model makes a lot of false positives. But when we include informations from the first previous frames, you can see that we can increase sensitivity and also increase precision. We can actually increase the precision by almost 20%. And the same thing for when we consider more previous frames. But you see that the sensitivity is going down a little bit. That's because when we consider more frames, the farther we go, that we will experience displacement for the polyps. So that's why the sensitivity is going down if we include more previous frames. Because the concatenation method that I implemented here is very straightforward. I just concatenate them by stacking the extracted features on top of each other. And this is the result for the specificity, and specificity measures the ratio of true negatives divided by the total number of negative frames in the test set. As you can see it again, when we only use the current frame to do the analysis, you see that the specificity is low. That's because of the false positives that the model makes. But when we include information from the first previous frame, you see that specificity increases by almost 21%. And the same thing, the same result can be obtained if we include more previous frames. So in this slide, I'm concluding the talk. As you can see it here, on-the-fly interaction between the capsule camera and the deep learning model can improve polyp detection. Wireless capsule endoscopy with an automatic video analysis can be an ideal solution for home-based colon screening program. And the measured end-to-end video streaming latency using UDP RTP protocol is about 46 milliseconds per frame. The deep learning, it can be an efficient way to analyze the video frames and detect the polyps in real-time speed. So the model that I showed you in the previous slide can analyze a single frame in 10 milliseconds per frame, which is quite high. Better performance can be achieved when information from previous frames incorporated. So that's the end of my talk. Thank you for your attention.
Thank you very much, Hemin, for your talk. We have room for a few questions from the audience, so please feel free. Anyone?
So while people are thinking about questions, maybe comments to us, I just wanted to, explain maybe one of the critical challenges that we are facing in this project. As you understood that the pill is moving, so having a real-time feedback, real-time in the sense that we believe at least a 5 to 10 milliseconds delay from the images are captured all the way to the transmitted to the cloud, done the analysis and send this information back should be sufficient before it moves to another part of the polyp, for example, or the part of the picture. The question now, as you would have seen from Hemin's presentation, was that now we have a total latency around 50 milliseconds. So if you assume that a camera that is taking 30 frames per second, so that each frame takes roughly, say, 30 milliseconds, and there is a camera that is moving, so every time you're exceeding this limitation, then most likely you would have moved from maybe one part of the cell to another part, another part of the polyps, of the cell. Then this might be, can be a potential problem because we might miss some polyps. So I think the latency is quite critical, at least for this application, and I think this is something that we have been discussing internally, and how to reduce the streaming latency using this UDP from 46 maybe down to maybe around 10 or 15 or 20 or something like that. So if you have any ideas or suggestion for us, that would be greatly appreciated.
I have one question which relates to the slide on the, what do you call it, recall of precision. Can you show that one again? Yeah, that one. No, the next one.
The previous one.
This one.
This one.
Yeah.
So wouldn't you go for the high sensitivity and sacrifice on precision, because you will always have a physician to double check the results?
So that is a good question. I think the whole idea, at least for this application, is that we don't want to involve any physician, no human in the loop. So the person, the person who is taking the pill everything is transmitted automatically to the cloud, and getting the information back and final results are maybe transmitted to a hospital or a physician. Of course, a physician can double check, but if there is overwhelming amount of false positive, then I think people would be, questioning whether the method is useful for them, because otherwise it's giving much more overload of work for them. So that I think, ideally speaking, it needs to be 100% for both of them, but we are not there yet.
Yeah, well, I was just wondering about the second in a row, which is just you look one frame back, and you increase your sensitivity a bit, you increase your precision by a lot, and doing one stop more, you will sacrifice the number of patients that you can actually detect. That you still need someone to look whether there are false negatives there.
Yeah. Yeah, I mean, that's true. But I think, this exercise that we have shown is, it is not complete work yet to say that. Maybe, we will not maybe use it in the clinic tomorrow. It's just to show that how to improve the precision at the same time, keeping within this 10 millisecond or maybe something like whole analysis per frame. So we are talking still on per frame. Ideally speaking, if we can reduce this down to maybe a few milliseconds, and also the transmission of the data maybe also to a few milliseconds, I think that will be good. Then, of course, this field is progressing, and I believe that, either us or someone else would be able to come up with some clever idea about how to improve this.
Cool, thanks.
Thanks, Edward.
Okay. We will have time at the end of the program to have more questions and discussions. So unless there are some burning issues just now, so maybe we should proceed with the next presentation. So